28th lecture, we talk about bipolar junction transistors. The meaning of the word junction should have become clear to you by now. A junction is created when two dissimilarly doped semiconductors are brought in close proximity of each other. For example, a P and an N type, two dissimilarly doped semiconductors are brought in close proximity of each other. A junction is created. The meaning of the word bipolar implies, the word bipolar implies that there is something called unipolar. Well, in a bipolar transistor, the current carriers pass through regions of dissimilar impurities. That is, carriers pass through P as well as N type of material, whereas there are unipolar transistors in which the current carriers, the electrons and holes, pass through only one type of material. All right, we shall not consider such transistors in this course. Such transistors in which the adjective is unipolar instead of bipolar are also known as field effect transistors, FETs. We shall not consider such transistors in this course. We will consider only bipolar because of their many advantages. Bipolar means that the current carriers have to pass through impurities, pass through materials of different characteristics, P type as well as N type. Now comes the word transistor. The word transistor was coined from a transferred resistor, where you delete this portion, then you get transistor. Transistor actually is an abbreviation for transferred resistor. And to understand why it is called a transferred resistor, suppose I pass a current I through a small resistance R, and by a device mechanism, by a solid state device mechanism, the same current is made to pass through a larger resistance capital R, then obviously the voltage developed, there is a transfer here. There is some transfer mechanism in which the same current capital I is made to pass through a small resistance at the input and a large resistance at the output. All right? Output, that means it is basically at least a two-port. At least a two-port. It is not a one-port. All right? A transistor is basically a two-port device in which the same current is allowed to pass through a small resistance at the input and a large resistance at the output. And this is why we call it transferred resistor. That is, from a small resistance it is transferred to a large resistance. Provided the current is a constant, then obviously the input voltage would be smaller than the output voltage. The output voltage will be capital I times R, and input voltage is capital I times small r, and if capital R is greater than R, then obviously the output voltage is greater than the input voltage, which means that there is amplification. This is the basic reason why a transistor is called a transistor. Transistor actually means a transferred resistor. Now, to implement this concept, that is to allow a current, the same current, to pass through a small resistance at the input and a large resistance at the output, the implementation is that you have two junctions. Instead of one, you have two junctions. And typically, you could have, let's say, a PNP configuration like this, where I am showing only a cross section. You could have two junctions like this, metallurgically prepared. They are not juxtaposed. That means you don't make a junction and then just make a contact between the two junctions. No, it is metallurgical fabrication, and how it is done we shall look at it in a moment. but you notice that there are two junctions here. One is this p-n junction and the other is this n-p junction. There are two junctions. Now you know that if the junction, this p-n junction is forward biased. If this p-n junction is forward biased, that is, this is connected to a positive supply and this is connected to a negative supply, all right, then current will flow through the diode easily and this current can be a large current. What is the resistance of this junction? When it is forward biased, the resistance is ideally 0, but it is of the order of tens of ohms, that is about it. On the other hand, if this same current, the current that flows through this junction, let us say capital I, if the same current is forced to pass into the other P region, if this same current is forced to pass into the other region and this junction is reverse biased, in other words this N is positive and this P is negative, alright. If I connect a battery across this junction in the reverse direction, very little current flows and therefore the resistance of the diode is high, ideally infinite. Now the current that passes through a small resistance in this p-n junction, if this same current is forced to pass through the high resistance of a reverse bias junction, then obviously we have achieved our purpose. That is, we have transferred a low resistance into a high resistance and therefore this will act as a transistor, and that is the basic reason why a transistor can amplify. But before we do anything, before we go into the depth of into a close examination of this current transfer or resistance transfer, let us see how such a device is made. And we shall illustrate only one of the methods which gives you what is known as a planar structure. Is this visible? Yes, I think so. Well, what is done is basically we need two junctions. So what is done is, first you start with a silicon, bulk silicon, which is N plus. N plus means it is, this plus stands for heavy doping, alright. So basically this is a silicon block, silicon chip or wafer which has been impregnated with N type impurity. That means either arsenic or phosphorus, the donor type of impurity, and the impurity has been introduced in a large dose. It is highly doped, so it is N plus. Now upon this N plus silicon is grown a lightly doped N region, lightly doped N region. All this all this colored stuff is not there. What you do basically is take a silicon which is N plus, and then upon this you grow by passing a gas of that material. There are other methods of doing this. You grow on this an N type region, that is the same silicon but lightly doped, less doped than this, alright. Then what you do is you subject it to oxygen so that the upper portion is oxidized to silicon dioxide, and you know silicon dioxide is an insulator, alright. Then you make selective etching, that means you make a mask with a window, and pass chlorine or some other etching agent so that this dioxide disappears, alright, the silicon dioxide disappears, and you allow a gas of, let us say, boron to pass. Then this boron will not affect this portion of the N type region. What it will do is it will diffuse inside the N region and create what? A P region, alright, create a P region. Then what you do is you oxidize again. You oxidize again and then make another window. All right. So what we have is on N, no, I'm sorry, on P, you have grown silicon dioxide and you have removed a part. All right. Then you pass a phosphorus gas, for example, so that what you do is you make another N region. So there is an N, there is a P, and then N and N plus, from which, well, let's look at this now. You have an N plus, then you grew an N, and by selective diffusion you grew a P type material. By another selective diffusion you made another N type material, and then you make metal contacts, gold or aluminium. Gold is the preferred one, you can also use aluminium. Now contact is here, one contact is here, that is below the substrate, that is a metal, and this terminal you call collector. Then one contact is here, that is this P type material. Well, the contact is, it could be circular, it could be rectangular, depending on the geometry of the wafer. So the contact is here, this is called the base contact, and the third one is this black region is also a metal deposition, that is, it is a contact with the N region, and this is called the emitter. All right. There are three terminals, emitter, base and collector, and in a simple diagrammatic representation we shall simply represent it by means of a block like this. We have N type, P type and N type. Then we have taken contacts like this, we have taken a contact like this and a contact like this. Okay. This is my emitter, this is base, this is collector. What is the use of N plus? Okay. N plus is almost like a metal. All right. N plus is almost like a metal, heavily doped semiconductor, and therefore its conductivity is very large, and therefore it behaves almost like a metal, and then it allows a metal deposition very easily. You see, whenever two dissimilar materials come in contact, there is a contact potential. All right. However, if you make a contact between gold and gold, there would be no contact potential. The differential of conductivity between the metal and the semiconductor, if it is lower, the contact potential will be lower. So the collector contact is made without a contact potential, and the reason is very clear. Collector is usually the output terminal. The collector is to handle large currents, and therefore it is necessary that the collector contact be as perfect as possible, and it should be able to collect current, and this collect carriers. This is why it is called a collector. So the collector is usually N plus and then a metal contact. Actually this whole region is collector, N plus and then the metal contact. The metal contact is between metal and N plus instead of N. It does not matter that much in the case of base and emitter, because very large currents will not have to be handled there. Very large power dissipation shall not occur there. Power dissipation occurs mainly at the collector. All right. Why? Because the emitter, as I have told you, one of the junctions, the emitter base junction, is forward biased. All right. And therefore a large current may pass, but at low voltage. So the product of voltage and current is low. All right. Whereas the collector base is reverse biased, that is a high voltage, and a large current passes. So the collector contact has to be as good as possible to be able to dissipate power. This also shows, it is an interesting question, it also shows that if the collector and emitter are interchanged, in theory, if I give you a schematic like this, there is no reason why C and D cannot be interchanged. But the fabrication is such that if you interchange this, then the capabilities of the transistor become limited. The power handling capabilities become limited. and therefore a transistor, in a transistor the collector is identified by means of a dot. If you see in the laboratory, the collector is identified, and the identified collector is to be used as a collector. If you use it in the inverse mode, that is emitter as collector and collector as emitter, the efficiency of the device becomes limited. Anyway, so you understand how it is fabricated. Such a transistor is schematically represented as a base and then a vertical line. This is collector and this is emitter. The emitter is, in order to distinguish between the collector and the emitter, okay, you have to distinguish between the two terminals. An arrow is added in the emitter, and the direction of the arrow has a very special significance. The direction of the arrow gives the actual direction of current at this terminal. The emitter current shall be in this direction. It gives the actual direction of the current, all right, and this shows that this is NPN. An NPN transistor shall be always like this, whereas there is nothing secret about NPN. You could also have a PNP transistor in which the base region is N, the other two are P. Then this transistor shall be represented by the same symbol, but the arrow shall now point inwards. It should be remembered that this is the actual direction of the current, the DC, the actual direction of DC. If it is AC, it doesn't make sense to talk of direction. Once it will flow like this, another time it will flow in the other direction, and so on. So it is DC that I am talking of, actual direction of direct current that flows. It flows out of this terminal, it flows into the transistor in the PNP case. Now let's look at the operation. How does it operate? And for simplicity, let's look at an NPN transistor. You must have been noticing that I always drew the base region as a narrow region as compared to the emitter and the collector, and it is indeed true. The base is a very thin region, and this gives the transistor its property. If it was very thick, then you would not get the property of amplification that we have been talking of. Now, as I told you, the emitter base, this is emitter, this is base, and this is collector. The emitter base region is forward biased. In other words, pardon me, this is wrong. Is it okay? All right. The emitter base region V, let's call it BE. Okay, the base is positive with respect to the emitter. This is forward biased. Now, and the collector base region is reverse biased. That means you have this polarity is okay, VCB plus minus. All right. Now, if you look at the barrier, potential barrier, there are two junctions now, NP and NP. If you look at the barrier, well, normally when there are no biases, suppose these two terminals are not connected, the transistor is left open circuited, well, then what happens is, let me draw it in a separate sheet. Let us say this is one of the junctions and this is the other junction. Then you know normally there will be a junction potential or potential barrier at both the junctions, and when the transistor is open circuited, both of these will be of height, let's say V0. Both of these. This is N, this is P, and this is N. All right. If the input junction, that is the emitter base junction, is forward biased, then this barrier shall come down. Okay. So, with forward bias it would be something like this. Forward bias, and this height shall now be V0 minus VBE, the amount of forward bias, alright, V0 minus VBE. On the other hand, the PN, the collector base junction, is reverse biased. So what happens? This potential barrier goes up, and this height shall now be V0 plus VCB. Alright. So on the left side the barrier is reduced, on the right side the barrier is increased. Now it is very easy now to explain what actually happens. Well, because of the lowering of the potential barrier, the electrons, which are the majority carriers in the n type, the electrons now get encouraged to go to the base. Alright. Electrons go to the base because of the lowering of the potential barrier. It is a forward bias diode, and normally if the other junction was not there, if it was simply P, then what would have happened? The current would have passed to the other terminal of the battery and go to the battery. Alright. But here the battery is between the n type and the p type, and normally this electron, when it enters the p type region, holes are available and they should have excuse me, they should have recombined. They should have recombined with the holes, which means that they would simply pass on to the battery. But this region is so thin that the possibility of recombination is very little, and most of the current, most of these electrons pass over to the n region. Most of these electrons, they enter the p region with a velocity, with a kinetic energy, and before they encounter a hole to recombine, well, they find themselves in the n region. It is so thin that they simply pass over, and therefore most of the electrons pass over to this region. All right. A little portion, a small number of electrons, let us say a fraction alpha, if we say that capital N number of electrons enter here, then a small portion, 1 minus alpha n, they recombine in the base region. The majority of it, alpha times n, they pass into the n region. What happens when they come to the n region? What happens? They go up the potential barrier. After all, these are electrons, and this is reverse biased. In other words, there is a battery with a positive terminal here which is trying to attract the electrons, and therefore they are encouraged to climb this barrier. Electrons can climb very easily. Electrons are encouraged to climb the potential barrier and pass to the battery, which in effect means the end result is that most of the majority carriers which start from the base, which start from the emitter, you understand the meaning of the word emitter now. They emit electrons. That is why it is called emitters. Well, most of the electrons emitted by the emitter, they pass over to the collector. Some of them, a small portion, cannot pass because they recombine. But most of them, in fact, alpha, this fraction, is greater than 0.98, greater than equal to 0.98. About 98% of the electrons pass over to the collector region, and a small portion, about 2%, they recombine in the base region. All right. Now, in terms of current, let me draw this figure again. This is P, N, N. This is the emitter region. Emitter base is forward biased, and this is reverse biased, which means that you have positive and negative here. All right. Now notice carefully what is happening. The this emitter, let me name them, emitter, base, collector. This emitter emits electrons. When it emits electrons, what is the direction of current? Current is in the opposite direction, and therefore the current, when the emitter emits electrons, a current IE flows out of the emitter terminal into the battery. All right. Now these electrons cross over to the end region. Some of them get lost, some of them recombine, which means that it is as if this positive terminal collects them, and therefore electrons passing like this, which means that a base current flows like this, I sub B. Is that okay? And most of these electrons are collected by the collector, which means that a current I sub C enters like this. So the relationship between the currents shall be I sub E by KCL, the total current entering, this is a 3-terminal device, the total current entering must be equal to the total current leaving. So I sub E equal to I sub C plus I sub B. Not only that, there is a relationship between I sub C and I sub E. I sub C is almost equal to I sub E, except for a small deviation, and therefore I sub C is equal to alpha times I sub E, where alpha is very nearly equal to 1, but it is less than 1. Alpha is less than 1, but very nearly equal to 1. Now in addition to this cause of current, there is another reason for a current flow, and this is the minority carriers. All right. This junction is reverse biased. Now you know that in a reverse biased junction there is a reverse saturation current, and what is the direction of this current? Obviously this is the direction of the current. All right. So due to I sub E, the current here is alpha I sub E. Yeah, I'll get wiser now. Alpha I sub E, this is due to the electrons, and due to the reverse biasing of the junction, this junction, there is a current ICBO, which normally in a diode we call IS, the reverse saturation current. Here we call it ICBO, collector base junction, and O stands for saturation. All right, ICBO, and therefore I sub C is alpha IE plus ICBO. These are the two basic relations in a transistor. All right, the directions, I'm coming to that. The directions have to be done carefully. That's why I first took the complicated case where the direction of the current and the direction of the majority carrier flow are opposite to each other. In a PNP it's much simpler. In a PNP transistor it is much easier to see in a PNP transistor what is happening. We have, this is positive and this is negative, and this is positive and this is negative. Therefore the current that enters now in the emitter region, i.e. it enters because the emitter region emits holes, not electrons. All right. So the carrier, the direction of flow of carrier is the same as the direction of the current. I sub E enters here, and alpha, well, let's see, I sub E enters here, a fraction of it goes to the base, 1 minus alpha IE, and the other fraction goes into the collector, which is alpha IE. In addition, there is a current. Which direction now? Same. That is I sub CBO. All right. So you can also now write a relationship for the base current. This is also obvious now. It is obvious that I sub C is equal to alpha IE plus I CBO. I sub E equal to I sub C plus I sub B, as in the NPN transistor. There is a third relationship which is obvious, that is I sub B should be equal to, yes? That is correct. I sub B must now flow in this direction. So I sub B is 1 minus alpha IE, then minus ICBO. Correct. These are some of the fundamental relationships of transistor operation. Yes? Here in this? Yeah, there is current due to minority carriers. No, this alpha E. Yeah, what is wrong with this? No, alpha is not the total number. Alpha is the fraction of the minority carriers. Well, these are minority carriers here. I'm sorry, these are majority carriers here, minority here. Then they become majority carriers here. In a forward bias junction, it is the majority carriers which take over. In a reverse bias junction, it is the minority carriers which take over. And therefore, we ignore the minority carrier current. All right? Okay. Now, let's take a transistor now symbolically. All right? Let's take a transistor in which, well, you know, this is the symbol for a transistor, an NPN transistor. Depending on the common terminal between the input and the output, there are three kinds of configurations. These are called common base, common emitter, and common collector. Well, a common base transistor is like this. It is simply a reorientation of the terminals. That is, you apply your input. What kind of a transistor is this? NPN, not PNP. The arrow goes out. Okay? So, the base is common between the input and the output, and therefore this is called common base, whereas this is the common emitter connection. Input is between base and emitter, output is between collector and emitter, and similarly you could have a common collector amplifier where the input is between base and collector and the output is between emitter and collector. This is the collector. This is called CC, common collector. This is CB, common base, and this is common emitter, CE connection. And the characteristics, the DC characteristics, the AC characteristics, the amplification characteristics, the switching characteristics, all of them differ depending on the configuration. And I must also point out that this is the most commonly used configuration, the common emitter, for its advantages. Let's look at these characteristics one by one. The common base, for example. The common base is, this is collector, emitter, and this is the base. Now obviously, in order to draw the DC characteristics, it is not a one port now. A diode is a one port, and therefore you draw current voltage characteristic, and that's it, nothing else. Here there are two ports, and therefore the characteristics now shall consist of two sets of curves. One is for the input and the other is for the output. However, you must consider the interaction between input and output. In other words, suppose you indicate this voltage, what should be normally the polarity of this voltage? E shall be negative and this shall be positive. So VBE we call it. This is B, VBE, B is positive, E is negative. What about this polarity? V, collector would be positive and this would be negative, so we call it VCB. C is the positive terminal and B is the negative terminal. What about the current? This current shall go out. Now note the nomenclature. We are using small I and the subscript is capital E. This terminology shall stand for the total current. Total current. Let me introduce this terminology right away. When I say total emitter current, I use this. The DC emitter current, I use this, DC. And the AC part of the emitter current, I use this. Alright, this is the terminology that we shall be using. The AC incremental part. In other words, small I subscript capital E shall be the sum of DC and AC part. This is the DC part or the quiescent part, quiescent, Q-U-I-E-S-C-E-N-T. This has a special meaning in the case of a device like this. Quiescent means in absence of any signal, in absence of an AC, if small I-E is equal to 0, then it is I, capital I sub capital E, alright. The small I sub small e is the AC or the incremental part. This is the signal part. This is the part that we wish to amplify, alright. Okay. Besides terminology, the current in the collector shall flow like this, and we call this I sub capital C. Obviously, the input characteristic shall be the characteristic of IE with variation of VBE. But then what is the effect of VCB? This also should have an effect. VCB should have an effect because the two junctions are in close proximity of each other. It is found that if VCB is very low, then the diode current, you understand that this is simply a diode. It is a base emitter junction diode, and therefore the characteristic should have been simply this. If I plot IE versus VBE, the characteristic should be like this. Alright. Now VCB does have an effect. If VCB increases, well, the diode current increase, but there is a small variation. This is the direction in which VCB increases. Alright, there is a small effect of VCB on the input diode characteristic. The input is obviously a diode, IE versus B versus VBE. The output characteristic is now extremely important. The output characteristic, that is IC versus VCB, alright, this is influenced tremendously by the emitter current. Why? Because majority of IC, most part of IC consists of a contribution due to IE. It is alpha times IE. There is a small contribution due to the reverse saturation current, that is, you know that I sub C is equal to alpha times I sub E plus I C B O. In other words, if I plot, now you also notice that this characteristic is independent of V C B. Okay, I sub C is independent of VCB, and therefore if I plot this versus VCB I sub c, it should be a straight line parallel to the VCB axis. It is only determined by the emitter current IE and I sub CBO. When the emitter current is 0, when IE is 0, a small current should flow like this, where this difference is ICBO. All right. When IE is, let us say, 5 milliamperes and alpha is 0.99, then the collector current should be 4. How much? 95. 0.99 multiplied by 5? 4.95, approximately 5. So the current shall rise to approximately 5 milliamperes. When IE, this curve is for IE equal to 0, maybe this is for IE equal to 5 milliampere, and so on. If IE is 10 milliampere, well, the curve will rise like this. So the collector characteristics shall be a set of parallel lines like this. That is, for equal increment of IE, there is equal increment of collector current. Is that okay? And the collector current, that is this level, is approximately equal to the emitter current. This will be approximately equal to 10. Is that clear? The common base characteristics are extremely simple. The collector current is approximately equal to the emitter current. The difference is because of the factor 1 minus alpha. Why does this arise? This arises because there is recombination in the base region. That is one reason why the base is made very thin, so that recombination can be ignored. All right?
Excuse me, sir.
Yes.
Sir, if the collector base voltage is greater than the breakdown voltage, what will I do?
Okay, good question. If the collector base voltage continues to increase, what color do I use? Let me use red, because it's a catastrophe. Right? If the collector base voltage is a reverse voltage, mind you, if it goes on increasing, then somewhere or other one of the two, either Zener or avalanche, shall take over, and then the current shall rise like this. One never goes to this region. Why? Because the power dissipation capability. Every transistor has a certain power dissipation capability, and no transistor is fabricated to dissipate the Zener power. No transistor, Zener only with diodes. This operation may be irreversible, and therefore one never goes beyond that region. So every transistor comes from the manufacturers with a spec of P max, that is, you must not dissipate more than this amount of current. Any other question? Let us look at the common emitter characteristic now. In common emitter, this is I sub E, this is I sub B, and this is I sub C. The input current is now IB, not IE. The input current is IB. But of course, this relation is valid, that is IE equal to I sub C plus I sub B, which means that I sub C is equal to I sub E minus I sub B. Is it okay? You also know that I sub C is alpha IE plus I sub CBO. All right. What we want to establish is the relationship between I sub C and I sub B. We don't want IE into the picture, because the input current is now IB, and therefore I write this as I sub C alpha I sub C plus I sub B, all right, plus I sub CBO. I want you to look at this carefully. what I have is I sub c equal to alpha I sub c plus I sub b plus I sub c bo, which means that I sub c, if I take this to the left hand side, 1 minus alpha shall be equal to alpha I sub b plus I sub c bo. Alright, that means the collector current is now alpha divided by 1 minus alpha times I sub b plus 1 by 1 minus alpha I sub c bo. Alright, look at this quantity alpha by 1 minus alpha. If alpha is 0.99, what is the value of this? 99, isn't that right? If alpha is 0.98, then 49. Okay, so it's very sensitive to small variations in alpha. This quantity is called beta. This quantity is named beta. Then you can see that 1 minus alpha is nothing but beta plus 1. Isn't that right? If I add 1 to this, I simply get 1 by 1 minus alpha. Agreed? And alpha is a quantity slightly smaller than unity, beta is a quantity usually much larger than unity, and therefore my relationship is IC equal to beta IB plus beta plus 1 I sub CBO. Take a specific case. I sub C equal to beta I sub B plus beta plus 1 I sub CBO. This current I sub CBO is usually a very small current of the order of microamps. Beta is of the order of 100. So 100 times microamps becomes 0.1 milliamps. I sub B is of the order of a milliamp and beta is of the order of 100. So this quantity becomes of the order of 100 milliamps, whereas this becomes of the order of 1 milliamp. Was it 1 or 0.1? 0.1. And therefore this quantity would be negligible compared to beta IB. And this is the ideal situation. Ideally, we don't want ICBO. Ideally, we don't want ICBO. Why don't we want it? Because ICBO is a function of temperature. This is one of the reasons. And the other reason is it does not change with IB. That is, if I inject a signal at the base, this quantity remains a constant. Nevertheless, this quantity is much less, I beg your pardon. The first quantity is much greater than the second quantity. This quantity is much greater than the second quantity. Now this shows a very interesting thing, that if you put a 1 milliampere at the base, at the collector you could get 100 milliamperes, which means that the transistor in the CE mode acts as a current amplifier. A transistor in general can amplify voltages because of transferred resistor, low current, low resistance to high resistance. A transistor in the CE mode can amplify currents by a factor of beta. Beta is alpha divided by 1 minus alpha. I want you to look at this figure before we disperse. I have shown here a common emitter. Is the figure all right? I have shown here a common emitter connection. Collector, emitter, base. And to the collector is connected a positive supply, VCC. It's a positive supply. There is a resistance RL here. And the current I sub C obviously is limited by RL. Alright, RL will have an effect on the current I sub C. In fact, VCE this voltage is equal to VCC minus the drop in RL, which is IC times RL, alright. On the other hand, a current I sub B enters here, and you can see that it contains two parts. One is the DC part or the quiescent part, and the other is the signal part, small I sub small b. Okay, and it is this current I sub C or this voltage VCE which varies in accordance with I sub B. This characteristic shows this more clearly. This is the line which gives a plot of VCE equal to VCC minus I sub C RL. It is superimposed on the characteristic curves, and the intersection of this with the quiescent condition, that is IB equal to capital I sub capital B, gives the operating point Q. And Q, the symbol Q, no longer for quality. Q is quality in resonant circuit. This Q is for quiescent point. It is from here that we will start our next lecture after the mid semester break.